Hello, everybody, and welcome to today's webinar presentation, Container Security, Key Challenges and How to Address Them, brought to you by Palo Alto. I'd like to introduce you to our presenters, Aksa Taylor and Ivan Melia. Aksa is a product manager with focus on cloud workload protection within PrismaCloud at Palo Alto Networks. Aksa leads development of features that aim at enhancing workload security and providing actionable data. Prior to that, she worked at Twistlock, providing technical consultation to large organizations on their cloud-native applications, security strategies, and deployments. Aksa lives in California and works from Palo Alto Networks headquarters at Santa Clara. Outside of work, she loves poetry and long drives through country roads. Ivan leads product marketing for cloud workload protection platform at Palo Alto Networks. Passionate about business, marketing, and technology, he focuses on product launches, pre-sales, and product adoption. Previously, he held product management and business development roles at Cisco. And with that, I'll hand it off to the presenters.
Thank you. Hello, everyone, and thank you for joining us on this webinar today. Before jumping into container security, let's take a look at how the technology has evolved in cloud-native application platforms. First, it started with virtual machines, or the traditional VM infrastructure, where you could define services and use VM machines for hosting them. But the challenge with VMs was the ease of scaling, the ease of deployment, the ease of going up or going down when you're using distributed environments, and the operation of deploying these infrastructure was difficult for a distributed application system. Containers resolve that with ease of deployment, ease of scaling, ease of multi-high availability. So containers became a popular option for deployment for infrastructures and applications. And then we looked into a further evolvement in the technology stack for containers as a service, Fargate applications, on-demand containers, serverless functions, and so on. So we see that the area of application development has been evolving across the tech. So people are moving from the traditional way of deploying applications into more minimalistic approach, where the architecture, where they don't have to worry about the underlying infrastructure or the bigger architectures, but only worry about code-dependent applications, and further abstract their deployment into a minimalistic approach of infrastructure. With this, let me hand over to Ivan. Ivan, can you tell us what you're seeing in the DevOps trends and market related to this development in the cloud-native sector?
Yeah, absolutely, Aksa. Hi, everyone. I would start with cloud migration. I think that's definitely the big one, the biggest driver. We recently launched the State of Cloud Native Security 2022 report and learned from the respondents that 2/3 of workloads will be on cloud by 2024. There's definitely acceleration here happening. I think it's a fantastic uptake. I think there's still room to grow because I think the sample population may not represent the market statistically, and that's why I think there's a lot of room to grow. As an example, on the far end of spectrum, I think about specialized workloads such as databases, banking backends, which are mainly written in COBOL. And we know that cloud service providers are investing heavily to simplify the workload migration to cloud. The second one is about containers becoming the norm. Containers as technology are not new. They date back to 1979. They came into forefront with Docker and creation of an ecosystem that flushed out these benefits and accelerated that adoption of various tools. When we couple containers with efficient container management tools such as Docker that came out in 2013, Kubernetes came out in 2014, when we couple this with microservices architectures and tools we have around automation and DevOps, we see a big trend in both re-architecture of legacy monolithic applications. They're jumping and riding this cloud-native wave, and they're doing this for clear benefits. Applications, the smaller pieces can easily scale up and scale out. And then we have net new applications that are benefiting from these trends from the get-go. Then the cloud-native came with the architectural considerations. We have formation of cloud-native computing foundation, and plethora of tools around DevOps, goal being CI/CD, agile development. We all want to ship fast. And the other architectural considerations around workload granularity and portability. And this is one of the areas that impacted security in our opinion. And then lastly, it's the complexity of security. That's our main topic today. It's about risks and countermeasures. Containers bring a ton of benefits, and with container usage, security is one of the top 3 challenges, and we'll talk more about it today. Now I'd like to jump into covering some of the key challenges we're seeing across the organizations. First, a growing number of entities to secure resulted in adoption of many point products on the market, and that ultimately drove the investment up, as well as maintenance and operational cost, thus creating some burden to different teams. Inevitably, this decreased the complexity of these siloed operations. So on one side, we have many different environments, IaaS, PaaS, containers as a service, and on the other, we have complexity increasing, and that's the issue because of this flexibility that was brought in effectively. We believe in a unified platform-centric approach. In the ever-changing environment, with adoption of what we discussed previously, DevOps, microservices, and APIs, I mentioned that the operational complexity is increasing, and that is the issue because the risk clarity is effectively decreasing, and because security is often part of a trade-off, such as for velocity, because again, we all want to ship faster. And then lastly, the security operations teams are the integral part in the grand scheme of things. And we believe security needs to be spread out across different layers and all the teams involved for a shared responsibility model, thus lessening the SecOps burden and allowing devs and infrastructure teams to incorporate security instead of it being a trade-off. So if we jump in our topic today, there are a number of aspects that make containers unique. They are fundamentally different from virtual machines and other ways to deploy applications, and the entire application lifecycle is changed with the container adoption. Aksa, what can you tell us about what's so unique about containers, and what are these lifecycle steps associated with building and deploying containers?
Sure, absolutely. So the thing about containers is that, or focusing on containers coming from the VM world or thinking about traditional application development, is containers are minimalistic. So they're usually single process entities. You write your Docker file or your YAMLs, and you're defining exactly what you want to achieve in that containers. So there's lesser dependencies on the underlying infrastructure to support it, because you're separating your application code from the maintenance code. So they are minimalistic, they're very declarative. So they're built from images that are machine readable, and several of these different OSs or different types of applications can be built on the same machine. So you still have that isolation between different applications while utilizing the machine resources to its maximum effectiveness by using containers. And they're predictable, because they are so declarative and written in a way that it's only designed to do what it's exactly the code application is defined in the Docker file and YAMLs. They are predictable. So when you bring in machine learning, we can learn from the static analysis of the images, behavioral analysis of the images, what the containers are exactly supposed to do. So it becomes easier if the security takes into account the static and behavioral analysis to define security for the containers, because then you know exactly what they're supposed to do, and any deviation from what they're supposed to do results in an anomaly or results in suspicious behavior that can then be tracked. And the other part of it is they're ephemeral. So you can spin up, spin down containers within minutes, within seconds. You can scale up, scale down. You can use orchestrators like Kubernetes and OpenShift. So it becomes really easy to maintain and distribute your application across multiple deployments, multiple clouds, agnostic of your cloud providers, agnostic of your underlying infrastructure or VM machines and such. So it becomes portability becomes easier, and deploying applications across distributed environments becomes easier. So this is how the container architecture supports applications or modern development of applications. Now let's take a look at what are the different steps involved in building and deploying containers. And I'm talking about a very generic view without getting into very specific details, and as an overall view, right? So you build your applications, meaning you write your Docker files or your image code. what the image is supposed to do. And generally, an image consists of a base layer, meaning your OS that you want to build your application on top of, and then you write your application code to run commands or network connections, web application commands, and such. So the build phase is most of the times we see that a CI/CD pipeline is used, like Jenkins or such tools are used for writing your images. So a developer writes a Docker file or an image, which includes what it's supposed to do, what is the base OS image to be used, what versions of packages to be used, how they're to be used, and so on. Once the build is completed, the next step would be you create your image, you do a Docker build of your image, and then you push that image into a registry or a container registry. So that would become your storage for your container images. And there are many types of registries out there. The cloud providers themselves have registries, so AWS, Azure, GCP, but there's also open registries like Docker Hub and other registries available to store your images. And then your next step would be, now you've built your images, you've shipped it. Hopefully you have quality assurance, making sure what you're building is secure. We'll talk about it a little bit more in our further steps. But then the last step would be you pull images from those hopefully trusted registries, and then start running them in the environments where you want to deploy these applications. So they can be on your own host, they can be on a cloud provider's host, they can be managed via orchestrator. And then your containers now start utilizing these images that you built and run your applications according to the code that you've written for them. So in general, we'll focus on how security, through this talk, we'll focus on how security can be a part of this life cycle and help you deliver more secure applications while you're building, shipping, and running your containers.
Thanks, Aksa. Now we're going to talk about the risks and countermeasures across the different stages of containerized applications. Yeah, Aksa, could you describe these stages at which risks occur?
Yes. So breaking down what we just defined about the different application lifecycle stages, first thing is build, right? That's where you're actually pulling what your base OS is going to be, what packages you're going to be using, how you're going to configure your image or container, and how it's supposed to run. It's very important to introduce security at this stage, and we'll talk about it a little bit more in the further slide. But this brings in risks. So if you use vulnerable images that have critical vulnerabilities, that have using vulnerable packages that have maybe DOS attacks, or there's an open door risk for your environment using those images. And then maybe embedded malware or clear text secrets. One of the bad configuration choices is to embed your secrets or passwords as a part of your image, because that's readable again, and it's a security risk. So how you define your images during the build stage is an opportunity for exposure. If you don't have proper posture management, if you're not using good compliance checks, if you're not really using good configuration posture, that's a risk. If you're using vulnerable packages, that's a risk. If you're embedding secrets and clear text, that's a risk. So it's really important at the build stage for security to dive in. And then ship. So when you're shipping or pushing these images to a registry, do you have proper authentication in page? Are you actually securing connection to the registries? What are you doing with the stale images in the registries? Are you making sure that you're purging your registries at a regular interval so that the stale images or the images with outdated packages and outdated vulnerable code is not used in your runtime environments? And then when you run those images, this is where majority of visibility risk and actual application risk comes into play. Are you continuously monitoring how your applications are running? Are your applications running exactly how you defined them to run? Or are you using maybe vulnerable code that's open to internet or gives access without authentication to external users? How is your vulnerability management at runtime? I mean, do you have configurations that are open to public that will give access to anyone who uses your application? So a lot of process monitoring, file system monitoring, all those risks get exposed at runtime, because now you're exposing your application to maybe the web or maybe to users without proper checks in place. And then one of the two other things that also are important to remember when you're thinking about container security is the environment and architecture. So not focusing on just the containers is not enough. It's also important to remember the environment in which you're running your containers. So if you're running, let's say, in orchestrators, maybe are there vulnerabilities in the orchestrator stack? Do you have proper privileges or admin control, access control distributed across your teams, or are you giving privileged access to all your users? And what type of auditing do you have in place on the environment where your applications are running? And then the last but not least is the architecture. So even though we've isolated everything, your containers are secure, your environment is secure, but if the architecture on which they are running is not secure, that again opens up an opportunity for exposure or an opportunity for exploitation in your environment. So if you're using, let's say, a host OS that has compromisable packages or vulnerabilities, then you're opening up a large surface area because all your containers are running on top of those hosts. So securing that architecture on which you are running these images also becomes important. So these are some areas to keep in mind if you're thinking of transitioning to container security, if you're in the process of containerizing your applications, or you're already using containers and thinking about security. Regardless of what vendor you choose or what security tool you use, these are different things and exposures and levels of security that you should have in mind when you're thinking of containerizing applications. With that, let's talk about each of these stages in detail. So let's focus on build.
Yep, let's start here and go one by one. Common risk in containerized environments is a deployed container with vulnerabilities due to image versioning with embedded vulnerabilities. So images are effectively static files that include all the components used to run an application. They may miss a critical update or simply can be outdated. And with container technologies, any changes needs to be made upstream, unlike traditional methods where software is updated on the host it runs on. In addition to these software defects, images may also have a configuration defect. An example could be an image which includes an SSH daemon, which exposes the production container to network risk, especially if that container was not meant to be SSH'd into. Malicious files provided by unverified third-party software could also be part of an image. After all, they are collections of files packed together, and the embedded malware could be used to attack other containers within the environment. Next one is about a practice of embedding secrets directly into the image file system. And this creates a risk because anyone with access to the image could parse the secret. These secrets could be credentials used by applications to enable secure communication between components. The last risk here we're seeing in the build phase is about a downside of the portability and ease of reuse of containers. There's temptation to run an image from an external unvalidated source, making it one of the most common high-risk scenarios. Aksa, what can you tell us about the countermeasures based on these different risks?
Right, so some of the things to keep in mind to avoid these risks is, first of all, introduce security in your build stage. Introduce security in your pipeline. So when you're building your image, the next step right after you build your image should be scanning your image. Scan your image for vulnerabilities and compliance as a part of your build pipeline, even before you ship it, even before you push it to your registry. An even more better option is to make this automated. Everything today is about automation, so security should be automated as well. So when your tool scans for vulnerabilities and compliance, if there are any critical vulnerabilities or compliance or any threshold that you as a security engineer set up for that application, if that threshold is violated, then the tool should automatically, by policy, stop the image from being pushed into the next stage of deployment, meaning being pushed into the registry or being used by a container in a runtime or anything. So Make sure that security becomes a part of your build, as a part of your immediate next step after you build your images. So use container-specific technology for vulnerability compliance and secrets management, because we talked about embedding secrets and such. So instead of relying on building your secrets inside your image, use secret management, vaults and such, and have proper authentication in place to use those technologies with your containers and images. And then also make sure that you use trusted sources. So whatever security tool you're using must ensure that the images that are being pushed to the registry only come from trusted sources. The images that are being pulled from the registry, or at whatever stage are being run in your environment, only come from trusted sources. Even if you're using a base OS image, make sure your base OS image on which you're building all your application code on top of is a golden image. Make sure it has no vulnerabilities or compliance, or as much you can minimize risks in that stage, minimize it, because afterwards, after you build the image, everything runs on top of it. So this is like your first stage, your foundational stage. Make sure your foundation is secure, make sure your foundation is strong by building secure images, introducing security in this part of your life cycle. Let's focus on ship. Ivan, do you want to highlight the risks containing?
Yeah, with the ship phase and registries. Registries are typically trusted as a source of valid approved software. And compromise of a registry can potentially lead to compromise of downstream containers and hosts. Registries may contain images used to run sensitive applications or access sensitive data. So here, insufficient authentication and authorization requirements can expose an attacker to intellectual property or any technical details of the application. So for the same reason as with this previous risk, if connections to registries are performed over insecure channels, the content of an image is subject to the same confidentiality risks. There's also an increased risk of man-in-the-middle attacks that could intercept that network traffic. And lastly, here with registries, they are a source location for all the images. So over time, registries will contain stale images that include vulnerable and out-of-date software, as we discussed previously. While this alone may not pose a threat, there's a risk of accidental deployment of one of these stale images. Aksa, what countermeasures we could propose here?
Yeah, so configuring your tools to only connect with secure registries. Try to avoid insecure registries. And if you're hosting your own registry, make sure they're secured by certificates. Avoid insecure connections. Also identify and prevent use of stale images in your registry. It's very tempting to not purge your registry and keep pushing images to the registry. But once there are images in your registry that are stale, meaning outdated data, or you don't have you have vulnerable images, there is, first of all, a risk that they can be pulled and used in the applications for runtime, but it's also not secure for your registry to have that kind of data as a part of the registry itself. So make sure you purge your oldest images and make sure that you, at a time, have maybe like 5 or 6 latest versions of your image, whatever you're using for your application. Also, always require authentication. I know it sounds very basic, but it's very important and also sometimes neglected. Try to avoid registries that are open to public, or if you're hosting images, don't host your images to public, because it's like giving your blueprint to your house. You're essentially giving all the open areas and the ways of entrance and exit and ways to break into your house. So avoid using that, or avoid giving such access to public, and only allow restricted and authenticated access to your registries. Let's now focus on the runtime.
Yeah, the threat landscape is definitely wide in this phase. The runtime software vulnerabilities are relatively uncommon, but the particular dangerous scenarios in which a malicious software can attack resources in other containers or the host OS. This allows an attacker to access other containers or monitor the inter-container communication. And in case of outbound network access, if a container in question is compromised or acting maliciously, allowing this network traffic may expose other resources in the environment to risk, such as network scanning to find other weaknesses. In general, egress traffic is more complex to manage in containerized environments because so much of the connections is virtualized between containers. Thus, the traffic from one container to another may appear as encapsulated packets without indicating source, destination, payload, and that sort of stuff. So tools that are not container aware are not able to inspect this traffic for any potential threat. Container runtimes typically expose certain config options to administrators. For example, on Linux container hosts, the set of allowed system calls is often limited by default to those required for safe operations. If the list is widened, it may expose both the container and the host OS to risk. Similarly, if a container is run in a privileged mode, it has access to all the devices on the host. So essentially acting as part of the host OS, impacting all the other containers. Next, risk is not so much about a container, but the application it runs in it. So let's consider a web application subject to cross-site scripting vulnerabilities, or a database subject to SQL injection. This would be considered a compromised container, and it can be misused in a way that grants unauthorized access to sensitive information. And finally, in this section, the presence of row containers is attributed to different development processes, where application developers may launch a container as a means to test the code. And if these containers are not scanned for vulnerabilities and misconfigurations, they are susceptible to exploits. They are an additional, often hidden risk to organizations as they persist without awareness of the development or even the security administrator teams. Let's move on to countermeasures for this area. Aksa.
Yes, great risks to summarize on runtime. One of the things about the container architecture that makes security complex but also easy if you have the right tools is the baseline behavior. The behavior of what you define the application to do, what you define that container to do, what was defined in that image. So it's really important for a security vendor or tool to use that to the advantage by creating a baseline of allowed behavior, that a container or an application is supposed to do. And then instead of writing thousands of lines of deny policy saying don't connect to this, don't talk to this application, or don't allow this process change, or don't allow this file write on the container or this directory, etc. Now you have a baseline that you can compare with and say this is what the application is supposed to do, and anything outside of this must be marked as suspicious activity. So you have more control over what your application is doing in real time. So it's very important to have continuous monitoring for such changes, for such suspicious activity for your containers. The other part of this is, again, automation, automating your security. So instead of just using security as an alerting system, like, okay, when something bad happens, let me see it, and then I'll think about what to do, you can use prevent operations. You can prevent deploying of crypto miners. You can prevent unauthorized access to outbound connections to different domains or different IPs that are in a threat list or are known to be malicious and such. So using prevention capabilities will help you not just use security as an alerting mechanism to just see when something bad has already happened, but avoid something bad from happening, to use prevent operations where necessary. And then use monitor at least the baseline security features that you must have is vulnerability monitoring, of course, vulnerability scanning, compliance scanning. Remember, compliance scanning is not just about the static scanning, which is the image scanning, but containers themselves also have some best practices that they should be checked against on how they're composed and running. So compliance scanning for your running containers. And then file system monitoring, process monitoring, network monitoring. These are the least minimum you must have as a part of your runtime security so that you can get visibility into everything that the application is doing. Besides this, additionally, you can have advanced controls like OPA or admission controller, access monitoring and auditing, or if you have a web-facing application, then it's also important that you have firewalls that understand the cloud-native infrastructure. So the traditional firewalls in this sense are not very compatible with cloud native applications because of how dynamic these environments are. Containers are ephemeral, so today you can have an Nginx container on node A, tomorrow if it scales up or scales down, you can have the same container or the same application spin up on a different node. So it becomes difficult to track by using static entities like maybe it's host IP address, etc. So your firewalls need to be more container agnostic. They need to know how the images are built, and regardless of which node an Nginx image comes to start on, the firewall policy must apply regardless of the underlying infrastructure or underlying OS and such. So having a firewall policy that's very agnostic to container applications and how they're designed and how they're deployed is also becomes very important if you're using web-facing applications. So these are some minimal requirements that you should think about when you're talking about securing your containers in runtime. In addition to this, what information can you send to your incident response teams? So yes, monitoring is great, prevention is great. Let's say if an incident did happen, then the in-depth forensics, what was the chain of events that led to that incident becomes important. So it's important for your tool to give that kind of visibility into internal forensics, the processes that were spun up, the access that led to it, the whole chain of events that may have led to an attack. So the importance of being able to forward this data to your CM tools, to maybe other providers or tools that you're using for your ticketing systems, being able to have APIs that are API calls that will give you this information on demand. So all these things come into play when you're thinking about securing your containers in runtime. So it's very important that the security tool you do use, the security vendor you do use, is keeping all these things in check or giving you this information, equipping you with this information to be able to take action. And there can be much more on runtime, but for the sake of this presentation, these are the minimal things that you should consider when you're trying to secure your applications in runtime. What can you tell us about the environment risks, Ivan?
Yeah, so this one is about the orchestrators. They were designed with environment-wide administrator access assumption, except that an orchestrator may be used to run applications by different teams. And in that case, if access is not provided on a granular level based on role and scope, potentially malicious or careless use could affect the operations of other containers managed by this particular orchestrator. They often include their own authentication directory service, which may be separate from the typical directories already in use within the organization. This can lead to weaker account management practices with orphaned accounts that lead to a system-wide compromise. The most critical risk we're seeing in a inter-container traffic in this area is the traffic from different applications sharing the same virtual network. If the two applications don't have the same sensitivity profile, such as front-end website application from the previous example, if that's being compromised, an attacker can leverage a shared network to gain access to a more sensitive applications behind this website. And lastly, orchestrator's job is to run workloads at scale and density, which means sometimes they can place workloads of different sensitivity levels on the same host. So in this example, we could have a web server and financial data processing workload on the same host. So critical vulnerability in the web server would put this financial data at risk. Aksa, what countermeasures we have available here?
Yes, so when you're thinking about privilege model or least privilege access model, there are different layers or different levels you need to keep into consideration. One is, of course, at the container level, like are you running containers as root, containers as privileged? What kind of access does your container need, and how much can you minimize that access? The second part of it is also your privilege of your users, so your IAM access, your actual user access. What level of administrative access are you giving to the users or your operators that are deploying these applications? But also it's important to monitor your orchestrator level activity. Orchestrators make this easy. There's many ways to audit your Kubernetes activity. Are there privileged pods being spun up and things like that? So wherever necessary, use pod security policies or least privilege model through access controls and OPA policies, admission controls in place. There are many tools that help you restrict that access, so it's important to use what is available with the orchestrators because there's many advantages to using orchestrators. You don't have to worry about high availability, you don't have to worry about scaling your application up and down by yourself manually. So there's a lot of advantages that these orchestrators bring. They also bring security, make ways for security to be easier if you have the right things in place, like your policy controls, your administrative access controls in place and such. The second part of it is like you talked about how workloads, sharing network or sharing sensitivity levels. Always separate your workloads by sensitivity levels and by network traffic according to those sensitivity levels. So let's say if you have a default namespace for something you're using for your default operations of the cluster, but then you have a prod namespace and a different dev namespace, make sure you use the isolation where it's possible to isolate your sensitive workloads, maybe your production workloads from testing workloads or QA workloads and other workloads. Not only in that level, but also within production. If you have a web-facing application that you're running on node A or a cluster A, you don't have to open that network access to the entire cluster, including your backend pods or containers. So wherever necessary, put the proper policies in place. So only the applications that need such access are able to be viewed or are able to be accessed by public. And your backend is protected with secure, authenticated access by only trusted sources or from trusted addresses and not open to public. So the way to think about this is if something XYZ got compromised, what is the level of control the attacker can gain in your entire system? As easy as this question might sound, a lot of risks and attacks that you read about in the environment or I mean in the industry are because of this chain of events. One thing gets compromised, and because there were no blockers in place, the attacker was able to get into the other areas of your organization, and so on. So it's important to build those blockers at each and every level. And orchestrators play a key role because they are actually spinning up these applications. They're actually maintaining your scaling. They're actually talking to different workloads, and they become that central point of your deployment and management of your containers. So securing your orchestrators with these best practices, and also make sure that you have visibility into vulnerabilities and compliance for your orchestrators as well. So make sure that your versions are up to date. You're not using a very old version of your orchestrator, whether you're using a cloud provider orchestrator or you've deployed it yourself and you're managing the Kubernetes, or you're managing the orchestrator yourself. Make sure you're always running the latest version of it, so you're more in step with the security assessments and patches and anything that may affect your older versions. So these are some best practices to keep in mind once you're defining your orchestrator security. And now last, but again really important, is the host risks. Ivan, what are the risks you've discovered from different researches?
Yeah, this is another crowded space with respect to risks. The first one on the list we have here, it's also an easy one. It's about optimizing the attack surface. That is minimizing the channels we have opened up for a potential attack, such as any network accessible service would provide a potential entry point for attackers, which effectively would add to the surface, to the attack surface size. Container-specific operating systems have a much smaller attack surface than that of a general-purpose operating system. For example, they do not contain libraries and they package managers that enable a general-purpose OS to directly run database and web server applications. They provide strong software-level isolation of resources. The use of shared kernel invariably results in a larger attack surface than with hypervisors because of the hardware-specific isolation, even for container-specific OSs. So overall, the level of isolation provided by container runtimes is not as high as provided by hypervisors. All host operating systems, even container-specific ones, would provide a foundational system component, such as the cryptographic libraries used to authenticate remote connections and the kernel primitives used for general process invocation and management. Like any other software, these components can have vulnerabilities, and because they exist low in the container technology architecture, they can impact all the containers and applications that run on these hosts. Organizations are exposed to risk when users log on directly to hosts to manage containers rather than going through an orchestration layer. And direct management enables wide-ranging changes to the system and all containers on it. And this can potentially enable a user that only needs to manage a specific application's container to impact many others. And lastly, insecure container configs can expose host volumes to greater risk of file tampering. For example, if a container is allowed to mount sensitive directories on the host OS, that container can then change files in those directories. And these changes could impact the stability and security of the host and all the other containers that run on it. Aksa, over to you.
Yep. I think one thing that becomes clear from these risks is it's important to use a container-specific OS. So even though your focus is on containers and you're deploying your applications in containers, if the underlying OS, if the underlying host is too vulnerable, if it's using libraries with too many vulnerabilities, if it's using packages and has configuration issues, you didn't put the right posture on the host that is running these containers, it becomes a very open area, very large surface attack for your applications, because once your host is compromised, it's easy to get into your containers, it's easy to get into your application code. So use container-specific OS where possible, and do not mix containerized workloads with non-containerized workloads, meaning if you're using a host to run your containers, try not to use the same host for running some Linux service as a part of your other applications, because then you're exposing, again, different types of attack surfaces. There's exposure from your containers, then there's exposure from your other service that's a non-containerized service running on the host. So do not mix your workloads. Leverage orchestrators to distribute your jobs across different hosts and such. Not only does it make it easy for you to maintain, but also it takes into account the securities, and you're updating your patches and versioning of your nodes, etc. becomes easier when you leverage such orchestrators, and run containers with minimal permissions on the underlying host. So again, root containers, privileged containers, try to avoid them as possible so that your containers are isolated from the host with as much gap as possible. So these were the 5 risks we discussed across the container lifecycle, and things to consider if you're trying to move into a containerized application, if you're trying to containerize your applications, or if you're currently running containerized applications. To kind of summarize, introduce security early in your lifecycle during the build stage. So make sure that you scan your images before you push them or before you start using them as a part of your build pipeline. And make that automated so that it fails whenever certain thresholds are compromised, or whenever certain thresholds that you define as a security persona are violated. And then when you're shipping your images, make sure that wherever you're storing your images, you have secure authentication to that storage. And not only that, purge your storage as well. So don't keep stale images. Make sure that you keep latest versions of your images that you're using for your applications. Make sure that you're using trusted sources. Don't just randomly deploy images from Docker Hub that you don't know the maintainer and could have crypto miners, malware, etc. So whatever, wherever you're storing, make sure that it is not open to public, you have restricted access to it, and you're keeping it secure. At runtime, only pull from trusted sources. You've done all that scanning in your build stage. You've done all that security posture management in your ship stage. But at the end, if you pull from an unauthorized source or an untrusted source, all that security goes in vain that you did in your shift left. So carry that security forward by only pulling and running applications from trusted sources. Not only that, when you're running applications, it's important to have continuous monitoring in place. Use prevention policies as possible. Make sure you have at least vulnerabilities, compliance, scans in place, and runtime file system monitoring, process monitoring, any connections to malicious activity. Have an automated security tool that gives you that baseline behavior of what your application is supposed to do, so that any anomaly or any suspicious activity outside of that is immediately reported, not only in the UI, but also available to be ticketed into your CM tools, into your other ticketing systems to be able to easily forward this data using either API calls or ticketing systems and forwarding and such, so you can take immediate action when necessary. Not only on the images or container side, but on the environment, if you're using orchestrators, it's important to secure your orchestrators as well. So make sure that you're following a good posture for your orchestrators using the latest version of your orchestrator versions and using least privilege model as necessary for access. And your underlying architecture, the host where you're running these applications, where you're running these containers, use container-specific OS, do not use mixed workloads, and use leverage orchestrators as necessary and isolate your workloads by sensitivity level and such. So these are the 5 areas that we wanted to highlight through this webinar. And now we would like to talk about what are the top 5 reasons customers choose PrismaCloud for their workload protection, whether it's containerized workloads, non-containerized workloads, or in any of the different stacks like serverless, Fargate, etc. So Yvonne, could you help summarize why our customers are choosing to go with us?
Yeah, thanks, Axa. Just a quick summary to hit on some points around the PrismaCloud. We strive to be tech agnostic and easy to use, so your security is never a trade-off, regardless of what role you play. We provide a deep integration at various levels of application lifecycle. Security is our core competency, and we pioneered the cloud-native security with PrismaCloud. There are many large deployments across our huge customer base that proves the benefits, and we believe we have the broad and deep vision of comprehensive cloud-native security platform that meets current market requirements. And on the next slide, I'd like to close with inviting you to visit our page at palotonnetworks.com/prisma/cloud. You could learn more about the product there. You could request a hands-on trial. There's an event next week that maybe some of you will attend. It's a Mobile World Congress in Barcelona. We will be demoing PrismaCloud there. This is traditionally telco audience at that event, so we chose a virtual packet core that powers 5G deployments. It's based on an open air initiative project where we'll demo some of these capabilities we discussed today.
Awesome, thank you, Yvonne. Let's now open the table for any questions that our audience may have.
All right, so if anyone has any questions, feel free to drop those into the questions pane right now. It looks like we do have a few already. So the first one is, in addition to container security, what other benefits does PrismaCloud provide?
Yeah, I can say that.
Oh. Yeah, please do.
Yeah, I could start. So PrismaCloud is a cloud-native application protection platform. It has broad security and compliance coverage. We have nearly 400 different out-of-the-box checks that we do on the compliance side. We secure the infrastructure, the applications and data, and also entitlements across the world's largest clouds. We also provide protection to air-gapped environments, to on-prem workloads as well. Aksa, would you like to add anything more?
No, and that's the beauty of PrismaCloud, because we don't force you into a specific architecture when it comes to security. Depending on how you deploy your applications, whether containers, VMs, serverless, Fargate, introducing security is also very native to that. So deploying PrismaCloud security is native to how you're deploying your applications. If you're deploying containers, then defenders run as containers. If you're deploying in serverless, then defenders are a part of serverless function. So it's very native to how you would deploy your applications as well.
All right, so our next question is, I'm a developer. What technical requirements do I need to meet before I can start using your workload protection capabilities?
Yeah, I can start with this one too. And I think it's a good question. In this case, yeah, it doesn't really matter what role the person plays. And I recently joined Palo Alto Networks, and I've seen firsthand how the learning curve is very mild, and we take pride in our UI UX work that really contributes to this. It's very easy to do things such as attach your cloud environment to to the product, instantly provides scanning. We have the radar view that provides a very good 360 overview of what's happening, at which point you can drill down into different vulnerabilities, different risks, and so on. So I would say the number one thing here is we got the great UI, UX, great documentation, and we're really set for success. So the number one thing really is to attach your environment to the product and enable that communication between PrismaCloud and your deployments.
Yeah, I'd like to add on to that is, since you're a developer, you're already developing your application. So let's say you are writing your Docker files as a part of your image development process. It's very easy to introduce compute, or PrismaCloud as a part of your security, because again, depending on how you're deploying your application, our deployment or PrismaCloud's deployment is native to it. So if you're running a containerized application, since you're already running containers, the way to deploy PrismaCloud is as a container. So your knowledge, your existing knowledge of the tech stack, in whatever way you are deploying or developing your applications, the same thing is expanded to using PrismaCloud. So you don't need additional knowledge on how to deploy or how to set up. Of course, there are great resources, as Yvonne mentioned, to help you with that journey, but it becomes easier because of how native we are with the underlying tech stack itself.
All right, looks like we have one last question here. Are there any other options for avoiding access to the public cloud environment?
It's a great question, and this is a project that AXA is leading, which is around providing additional implementations of different architectures. So we have today agent-based, defender-based, which is the one we typically have for providing protection, but providing visibility, something we call agentless. AXA, do you want to say a few more words about this and what sort of visibility and benefits we provide with agentless, in addition to really deep protection at the runtime level with our defenders for agent-based protection?
Yes, absolutely. I'm very excited about this one. We recently launched agentless security, and the idea is, as you define, as you explore your options to secure your containers and secure your applications in general, you shouldn't be tied in with a specific vendor. And recently, specific vendor architecture. And recently, there was a lot of debate on, is agentless the better way of doing it, or is agent-based the better way of doing this? And it's not really a debate, and not really the right way of looking at the problem. The problem is, if you're trying to scale in a distributed environment and you don't have the access to deploy agents, then of course it's important to still get visibility into those resources that are running in your cloud. So agentless is a mechanism by which, without having to SSH into your machines or deploy anything as a part of your running instances, you still get visibility because we talk to the cloud providers. We get a list of your instances or resources running in your environment and scan those resources without deploying agents to bring you that visibility when you don't have access to deploy agents. On the other hand, it's complemented with agent-based architecture as well. So let's say you are scanning your cloud account. Any changes in the cloud account, new host that gets spin up, agentless scanning is enabled, everything's being monitored. The next step is you have some very sensitive workloads and sensitive hosts or sensitive instances where you're running sensitive applications and you want additional security, visibility, runtime protection, and prevention. That's where agents come into play. So you deploy defenders, you deploy your agents and get that in-depth visibility. So now agentless and agent-based architectures are working hand in hand to give you breadth and depth together instead of you having to compromise on each. So I'm really excited personally as a product manager for that, and also they're seeing a lot of interest from the community and industry. So agentless will be a parallel track we will keep investing in and add more features to and enhancements to. So please reach out to us and we'll be happy to share more details on our roadmap and what we already have available in that regard.
Thanks, AXA.
Yeah, thank you so much, AXA. That sounds fantastic. And with that, we've reached the end of our webinar. So DZone would like to thank AXA and Ivan for a great presentation. And DZone would also like to thank Palo Alto for providing the audience with a great webinar. And lastly, thank you to everyone who attended today. We hope you learned something new that will help you in your developer career.
Thank you, team.
Thanks.